Hi, I'm Suraj. I'm a PhD student in the Strong Field and Attosecond group of Giuseppe Sansone from the University of Freiburg, and I'm also a member of QU-ATTO. Today, I'm here to talk about Attosecond correlation metrology and seeded free electron laser. If Attosecond pulse trains have been demonstrated in FELs, and this gives us a big advantage that we can use these powerful sources to access to the XUV nonlinear phenomena. And also, this allows us to shape and characterize attosecond pulse trains as we talk later. And we specifically do our experiments in the Fermi free electron laser at Electra in Trieste. And as you can see from the image, the circular part is the synchrotron, and the linear part is a linear accelerator, and this is the undulator hall where the radiation is generated, and this is the experimental hall where we sit and do our experiments. And Fermi is a seeded free electron laser, which means it uses a seed laser to produce XUV radiation. Apart from the other characteristics, FEL allows us to generate coherent multiple harmonics. And if you take 3 such coherent harmonics and add them up, in time you have an attosecond pulse train. And the important thing to notice here is the distance between 2 attosecond pulses is 880 attoseconds. Just remember this value because this will come handy. And the next question arises is, how do we measure the attosecond pulses? The initial idea was to do photoelectron interferometry. As you can see from the scheme, by the absorption and emission of NIR photons, we reach the same energy level, leading to interference. And if you consider all such coherent pathways, we are supposed to get a photoelectron spectrogram like you see here. But as I said before, the distance between 2 attosecond pulses, the time period between 2 attosecond pulses is 880 attoseconds. So we need a delay between XUV and IR which is smaller than this time period to see these oscillations. But FELs generally have a timing jitter between the XUV and IR. In the case of Fermi, this is plus or minus 3 femtoseconds. And because of this jitter, what we will be recording is just noise, as you can see here. So since we cannot improve this jitter, we implemented a new method called correlation-based reconstruction of attosecond pulses, in short called COBRA. In experiment, what we do is we compare the intensity between the 2 sidebands, and this correlation will lead to the formation of some Lissajous figures. And the shape of this Lissajous figure depends upon the phase difference of the harmonics. As you can see here, if 3 of these harmonics are in phase, we get a really nice positive correlation. And if we change the phase of one of the harmonics, we see that if it changes to pi by 2, what we get is a circle. And if it changes to a pi, what we get is a negative correlation. If we take this into experiment, in the experiment, we have 3 harmonics, harmonic 9, 8 and 7. And in order to change the relative phase between the harmonics, we use phase shifter, which is nothing more than a magnetic chicane. What it does is, it delays the electronic bunch with respect to the radiation, which in turn will create a relative phase difference between the harmonics. And as you can see here, our correlation plot moves from a positive correlation to a negative correlation as we change the phase of the harmonic 7. And on the left, as you can see, if all the harmonics are in phase, we have a really nice attosecond pulse train. But as the relative phase between the harmonic changes, for example, if the relative phase is pi by 2, we still have an IPT, but we generate some satellites as well. And if the relative phase between them is minus pi, then we have not so nice attosecond pulse train. This experiment proves us that by changing the phase, we are in total control over the synchronization between the 3 harmonics, and we are able to shape and reconstruct attosecond pulse trains. Thank you for your attention.